In this video, I am going to discuss as to how a nucleophile and an electrophile can be identified. So let us look at how to identify a nucleophile. So nucleophiles and electrophiles are the reactive intermediates, and identification of these nucleophile and electrophile is important to understand any reaction. So the first step in understanding any reaction is finding out a nucleophile and an electrophile. So what is a nucleophile? So the nucleophiles are the negatively charged or the neutral species with a pair of electrons. These are the negatively charged or the neutral species with a pair of electrons. And the most common type of nucleophiles have a non-bonding lone pair of electrons. Like we have one lone pair on the nitrogen and two lone pairs on the oxygen. So that is nitrogen, we have one lone pair. And on the oxygen, we have two lone pairs. Two lone pairs on the oxygen. The typical neutral nucleophiles with lone pairs are ammonia, amines, water, and alcohol. So nucleophiles with a lone pair of electrons are ammonia. So here we have a lone pair of electrons on the nitrogen. And this is a tertiary amine, lone pair of electrons on the nitrogen. And the alcohol, ROH, two lone pair of electrons on the oxygen. And the water molecule where we have two lone pairs of electrons. But the other atoms in the periodic table which carry lone pairs and are good nucleophiles are phosphines, where we have a lone pair of electrons on the phosphor, and thiols, two lone pair of electrons on the sulfur, and the sulfides, again, two lone pairs on the sulfur atom. So the nucleophiles with a negative charge. And these are the anions which have lone pairs and are often good nucleophiles. And the anionic center is usually the oxygen, sulfur, or halogen. So we have bromide ion, Br minus is a nucleophile, and OH minus is also a nucleophile. And the most important carbon nucleophile with a lone pair of electrons is the cyanide ion. So in the cyanide ion, that is Cn minus, we have the negative charge on the carbon. So though the lone pair of electrons are there on the carbon atom as well as the nitrogen atom, the nucleophilic center is the carbon, as the sp orbital of carbon is of higher energy than that of the electronegative nitrogen. That is, the negative charge will be on the carbon. We have the nucleophiles with a CC double bond. So molecule can be nucleophilic without a non-bonding lone pair. So that is in the case of alkenes, where we have the double bond. So these pi nucleophiles are present in alkenes and aromatic rings. So we have an alkene. So generally the alkenes, they undergo electrophilic addition reaction. So because this pi bond is nucleophilic in nature, therefore the electrophile will attack on the alkenes. And the nucleophiles with a sigma bond between electropositive atoms. So here we have a borohydride, which is a good nucleophile, and it will attack on the electrophilic carbonyl compounds. So this is BH4 minus ion. This is the borohydride ion. And next we have the organometallic compounds. So organometallic compounds are those where the carbon is attached to a metal. So in the case of organometallic compounds, since the metal is more electropositive, all these alkyl groups, so the carbon is a source of carbon ion and they act as nucleophile. So in the case of methyl lithium, that is methyl lithium is CH3, linked to a lithium ion. So the CH3 is a source of anion, that is carbon ion, methyl carbon ion. This is the methyl lithium. And the next is the nucleophiles donate electrons from available high energy orbitals represented by one of the following. Like here it is ammonia, a neutral molecule where we have lone pair of electrons, and the lone pair of electrons are donated to the electrophile. And here we have an anion. This is a bromide ion, Br minus, and here the electrons are donated to the electrophile. And we have a pi bond in the case of alkenes and the aromatic rings. So the electron movement is shown by the arrow, which is donated to the electrophile. And we also have the organometallic compounds, that is methyl lithium, where this is a source of the CH3 minus is a source of the nucleophile. So the curly arrows, so these are the curly arrows. This represents the electron movement away from the nucleophile. And these electrons are donated to an electrophile. So, but how to identify an electrophile? These electrophiles are neutral or positively charged species with an empty atomic orbital or a low energy anti-bonding orbital that can easily accept the electrons. So the simplest electrophile is the hydrogen cation, that is H+. So H+ is hardly ever found, but almost any nucleophile will react with the H+. So let us look at an example where we have dimethyl sulfide. So dimethyl sulfide is a nucleophile because it has a lone pair of electrons, and this lone pair will attack, or it will give the lone pair to the bromine molecule, as this is shown by the curly arrow. And the bond between the bromine is pushed on to here, where a new sigma bond is formed between the sulfur and bromine. So here bromine is an electrophile and dimethyl sulfide is a nucleophile. And the next is we have a borohydride anion, which is a nucleophile. So this hydrogen along with the electron pair will attack on the carbonyl carbon. So if you look at the difference in the electronegativity between this carbon and the oxygen, since oxygen is more electronegative, so the bond pair of electrons is pushed towards the oxygen, and we have a partial positive charge on the carbon. So that is, it is an electrophilic carbon. So this borohydride anion, which is a nucleophile, will attack on the electrophilic carbon of the carbonyl compound. And we have a BH3, and a new sigma bond is formed between this hydrogen and the carbon. And the pi bond is broken, but this sigma bond remains. And the next is the electrophiles accept electrons into empty low energy orbitals represented by one of the following. So here we have a positive charge hydrogen, a positive charge representing an empty orbital. So it will accept the electrons from the nucleophile. And a neutral molecule like boron trifluoride with an empty p orbital, and a double bond which is attached to an electronegative element like oxygen, and a single bond to an electronegative element.